Hello, and welcome to week 13. Our topic for investigation this week is glaciation, and we're mostly going to focus on continental glaciation. But with that said, let's dive in. Okay, so what are we looking at here? This is a map of the upper Midwest. I hope you can see the outline of Minnesota here with the Great Lakes. And this is just to give you a taste of what is to come. The yellow and green areas effectively show the extent of ice during a time chunk that gets called the Wisconsinan, or the Wisconsin Age, which is part of the Pleistocene glaciations. And these green areas are basically piles of sediment that stand up above the rest of the landscape that tell us that ice pushed it there, and probably ice stayed next to it for a while as more sediment was deposited. This area in here in this sort of pale gray-blue color shows the extent of one of the multitude of earlier glaciations. So that's just a teaser. What I want to focus on now is how we're going to investigate glaciation. So we're going to start by looking at glaciations and time. Then we're going to briefly review the components of the cryosphere. We'll talk pretty briefly about alpine glaciation. Then we're going to dive into continental glaciation and some of the landforms associated with continental glaciation. That's, in other words, what we're seeing in the upper Midwest. And we're going to focus in particularly on the history of ice lobe advance and retreat in the upper Midwest. Why isn't it advancing? Okay, so first of all, let's just think really big picture. So the global geologic record of glaciation. So the text here points out that over the past 600 million years, we, the Earth, in other words, has experienced climates that vary from really warm, referred to as greenhouse state, to conditions of cooling or icehouse state or condition. Now, let's move over to the diagram at the right. On the right-hand side is cold, so that would be our icehouse conditions. And on the left-hand side is warm, in other words, our greenhouse conditions. And we've essentially got a time scale here, and it actually goes back to or into part of the Archean, all the way through up till now at the very top. So what does this graph show? It shows 1, 2, 3, 4. Oh, I missed the Pleistocene. 1, 2, 3, 4, 5 major glaciations. And that's these peaks shown in blue. And there are also some very significant warm periods. Now, there's one thing I want to address straight away, and that is the issue that there have been times in the past where it has been much warmer than now. And that is absolutely true. A lot of people end up coming back to climate change and global warming discussions by saying, well, it's been warmer in the past, so what? Well, that was a long time ago. And we people have adapted to live in the climate that is essentially our climate today. We could not survive it during any of the time periods when it was significantly warmer. So yes, it is, we are in a cooler period, relatively speaking now, but that is what we and life as we know it has adapted to or has developed based on our current conditions. So how do we know all this? We look at ancient glacial deposits. There's also a whole bunch of geochemistry that can be done that also ties in with these peaks showing cooler time periods. There's features or processes like weathering, chemical weathering, tell us a lot about the climate conditions, whether it's warm or whether it's cold, because different minerals or rocks will weather in different ways depending on the temperature. So let's think now specifically about these Pleistocene glaciations. So before we worry about the text, look at the diagram that we are familiar with. I hope you remember the Phanerozoic. It's the big time chunk that started, well, on here it's 570 million years ago. Gets divided into Paleozoic, Mesozoic, and Cenozoic. And the Pleistocene's way up here. So we're going to move over to a diagram or a time scale that focuses on the Cenozoic. That's the time chunk from 65 million years to now. So down at the bottom here, 65 million years ago. This entire time chunk is called the Cenozoic. It gets divided into the Tertiary, which goes from 65 million years to 2.6 million years. And I'll have that discussion with you in a moment. The time period between 2.6 million years and now is called the Quaternary, and it is divided into the Pleistocene and the Holocene. Now, so the Ice Age or Ice Ages, the most recent period of ice advance was during the Pleistocene. Now, let's have the conversation about when did that start. So we now know that the Pleistocene started sometime around 2.6 million years ago. And then it lasted until, well, this depends on partly where one is and how one decides to say it stopped. 15,000 years ago, is it 11,000 years ago? But technically, the end of the Pleistocene was 10,000 years ago. And our current time chunk is the Holocene, 10,000 years through until the present now. So you will see all sorts of numbers in whatever literature you look at for the base or the start of the Pleistocene. Here, I love this diagram, so I kept it, but the 1.8 million years is wrong. We now know it's 2.6 million years ago. So just bear that in mind. And that's because we have learned a lot from studies of deep ocean cores and part of the sedimentary sequence in the Mediterranean. So we've now established when the Pleistocene glaciations took place. where the ice built up in the North America, all across Europe, and also in places all the way through Asia, and was more extensive in places in the southern hemisphere as well. Did you know that there were and there are still tiny remains of glaciers in Papua New Guinea, which is almost on the equator? There were also glaciers on Mauna Loa in Hawaii. If you go up to see the telescopes, you drive along the road and there's volcanic rock there that has glacial grooves or striations on it. Amazing. Okay, so what makes up the cryosphere? The cryosphere is the word we use for our frozen world. So there's ice sheets, ice caps, and they are responsible for continental glaciation. Then outlet glaciers, valley or alpine glaciers, ice shelves, icebergs, sea ice, and then permafrost as well. So ice sheets, here we are. And this picture is from Antarctica. Antarctica is covered by two ice sheets, the East Antarctic ice sheet and the West Antarctic ice sheet. What we're looking at here is the edge of the East Antarctic ice sheet, where it starts to drain through the transantarctic mountains towards the Ross Sea. So what you're looking at here is what we call an ice fall. So ice behaves kind of like water, except it's frozen water, and it will move by gravity down steep slopes, and it will crack and break and fracture to make a really highly crevassed area as it moves downslope through the mountains. So let's dive into exactly what ice sheets are. So on the right, we've got a map of Antarctica. So here, where I'm outlining with my cursor, is the East Antarctic ice sheet. And the West Antarctic ice sheet is over here. Now, if you do geography with your students, Antarctica is really confusing because of the cardinal directions and the naming of what is East Antarctica versus West Antarctica. So I'm not going to dwell on that. Let's focus in on just ice sheets. So an ice sheet is ice that completely covers land, and that ice isn't constrained by topography, the shape of the land. So ice sheets exist on a continental scale, so they can be thousands of miles, as indeed they are in Antarctica. Now, in Antarctica, I mentioned there's the transantarctic mountains. They kind of stick up, and they are what the East Antarctic ice sheet drains through. There are also some places where there's bits of rock sticking up. So if we were to go over to Wilkes Land, and many other places, these areas of rock that stick up above an ice sheet are called nunataks. Anyway, large continental scale ice sheets, East Antarctic ice sheet, West Antarctic ice sheet. Other ice sheets are the Greenland ice sheet. We use the term ice caps for basically mini versions of ice sheets. They also, or the ice in ice caps also is unconstrained by topography. That means it completely covers the topography. It's not like it's a river of ice flowing within a valley. So tens to hundreds of miles. Now, any ice sheet has areas where there is the snow collects. These are ice centers. This is usually where the ice is thickest. And here, this heavy dashed line here kind of shows those areas of thick ice. And the ice flows away from those ice centers. Now, ice caps, I've already mentioned that they're just smaller versions of ice sheets, and often, such as in Baffin Island over here, they're the remnants of a once more extensive ice sheet. Here we are in Greenland. Here, this is the Greenland ice sheet. And just like in Antarctica, there are ice centers or a main ice center, and the ice flows away from that ice collection center. Once we get to Iceland, which is right here, there's a small ice cap in Iceland. And that's really interesting because the ice actually interacts with volcanoes that are underneath it. So that produces a whole bunch of interesting scenarios. So we've looked at ice sheets and ice caps. And now let's just go back to that ice that flows from the ice sheet. So here we are once again in Antarctica, and we're looking up essentially in the distance towards the East Antarctic ice sheet. And what we're seeing here is a outlet glacier that is flowing, yes, through a valley, and it reaches the Ross Sea. And what's hard to appreciate in the image on the left is that once it reaches the Ross Sea, which is right here, that ice ends up flowing out into the ocean and floating on top of it. So these outlet glaciers feed ice shelves. So this here is part of the Ross ice shelf, and it is basically a floating tongue of ice that's fed by an outlet glacier that comes from the East Antarctic ice sheet. So here in the writing, ice shelf is floating ice, and it's fed by on-land ice. So that ice will move through a valley as an outlet glacier from an ice sheet. Now, in front of this ice shelf, that's where we see icebergs. So when this ice shelf breaks up, it will basically produce these icebergs. And some of the icebergs that have been shed by ice shelves have been absolutely enormous, the size of Rhode Island, you know, huge things like that. Now, one thing that it's very important to appreciate is that sea ice is very different to ice shelves. Sea ice is the frozen surface of the ocean. So when it gets cold enough for the ocean water to freeze. So the extent of sea ice will vary seasonally. And what I want you to do is look at the image that I'm outlining here. In white, you can see probably some multi-year ice, but in this slightly darker, bluer area, that will be much thinner single-year sea ice right in here. And the sea ice constantly moves around. There will be openings that open up and then they close again. A great movie to watch is Shackleton's endurance. You really get a feeling for what the southern oceans and existing on an ice shelf or sea ice can be like. So sea ice can be single year or multi-year sea ice. Just depends on how much melting there is any one year. And there are hundreds of terms for different types of sea ice. If you look up here at the right, this is a kind of pancake ice. Well, that's the term given to it. And in places like Antarctica, or once one goes to the northern polar regions, one needs an icebreaker if during the spring or the one time of year when it melts, one is trying to get a resupply ship in. One thing I need to point out that I didn't have a slide for is what is the difference between the Arctic, northern polar regions, and Antarctica, the southern polar regions. The northern polar regions, the Arctic, is ocean surrounded by continent with polar bears. Antarctica is a continent covered by ice, surrounded by ocean with penguins. All right, so we're going to take a brief tour now through valley or alpine glaciation. So over on the left, in valley or alpine glaciation, and it's called alpine glaciation because the features were first described in scientific literature by people working in the European Alps. So these terms get used interchangeably, valley and alpine. So the ice is constrained by topography. So it flows in a valley-like feature, such as shown in the image in the upper right, or hopefully you can convince yourself in the image over towards the left. So essentially we have a river of ice that flows down valley between steep rock walls, and it flows from the area it accumulates in higher up in the mountains down to lower areas. And valley glaciers range in length from 1 kilometer. There's some very short ones in New Zealand, going from the crest of the Southern Alps westward to the west coast of New Zealand. And there's some enormously long glaciers in the Himalayas and European Alps. So what I want you to do is just look here at these alpine glaciers. The white area is fresh snow. What you can see are these cracks that show through that fresh snow. These are crevasses or cracks in the ice that has been forming. And depending on how the glacier is being stressed, they will be either transverse cracks or longitudinal cracks. Something else I want you to notice is these dark lines in this glacier. This glacier in the upper right is actually flowing away from us down valley. And these are what are called medial moraines. That's rock debris that collects on the edge of a glacier, falls down the valley walls. But then if we have a multitude of tributary glaciers, what would normally be on the edge joins in the middle to form a medial moraine. So here we know that this glacier that we're looking at has at least 2 tributaries, one over here to the right, one to the left, and one basically coming right down from here. So there's a couple of other concepts we're going to think about now. How do we make this glacier ice? Now, we have a lot of experience, maybe not this year, with ice and snow. So this won't be foreign to us. So first of all, we have snow it accumulates and it becomes ice, and then it moves downslope as a consequence of gravity. Look at the diagram in the lower right here. So we have our snow, and then once it's collected over time, it becomes granular snow. And then it gets reduced to these chunky globs that we call, that's non-technical, that we call firn. And it eventually becomes compressed into glacial ice. How long does that take? Well, anywhere from 3 years to 5,000 years. You may wonder, why so long? And where do we see these differences? Well, it actually turns out that in areas where there's more melting and more rainfall on a glacier is where that happens more quickly. And that's because the liquid water can percolate down through the ice and freeze and help facilitate this transition. Whereas in a place like Antarctica, for example, it takes much longer to make that glacial ice. So we have, if we go to this upper diagram here, we have our zone of accumulation. So that's where it all starts. Our snow falls, it tends not to melt. Somewhere partway down the valley glacier, there'll be what we call a snow line. And that effectively is the line that marks where snow above that will stay, won't melt. Down below that, it melts and disappears, or it will, it melts, or it sublimates, or it sublimation, melting. I'm forgetting the other phase transition. Anyway, so up here in this zone of accumulation, the processes that we've talked about down there take place. And basically, once you've got enough ice, it moves down slope because of gravity. And it moves sometimes by sliding, and there are also some zones in there that fracture or break. And that's what makes these crevasses. Down at the front or the toe of a valley glacier, that's where we have melting taking place. This gets called the zone of wastage or ablation. That's where all that ice either breaks off or melts. So this leads us to considering something that's called the glacial budget. So this is basically about whether the ice front, that's the position of the ice in the down valley direction, stays where it is, moves back up valley, or moves down valley. So we'll come back to that in just a moment. So the glacial budget. Accumulation has to be greater than wastage, which means melting and or sublimation. If, and this isn't written down here, if we want the valley glacier to grow and advance, and I've already mentioned how it moves, the ice moves internally by what we call plastic flow. That means it just flows, but there are also some zones of fracture. Now, what is really important to get your brain around is that regardless of how much wastage or ablation there is, the ice will always be moving forward. If we have a retreat, that's when the ice front moves back up valley. The position of the ice front moves from here up valley away. The ice is still physically moving forward. it's not like a car. It doesn't just go into reverse and go and back up. The ice is still moving forward, but what's happening is there's a lot of ablation at the front. So the position of the toe or ice front moves back up valley. And that's what's happening here. You can see a small ridge that is sediment that was deposited by the ice, but then there's been melting. There's a bit of a lake in here in front of the ice. We call that a proglacial lake. Okay, so I've already started talking about advances and retreats, but here's some text to help you along with that. So if we have a retreat or a recession, we talk about the ice receding, and that means that the position or toe of the ice front moves back up valley. If, on the other hand, there is an advance, that means that the position or toe of the ice front moves forward. In other words, advances down valley. Now, I'm introducing the glacial budget and retreats and advances in the context of alpine glaciers, but continental glaciers do the same thing. They have lobes that extend out from the main body of ice, and those ice lobes retreat and advance based on whether we've got more or less accumulation versus ablation. And then there's the situation of stagnation, and that's just when there's no net change in the location of the toe. So you may wonder how fast ice moves. So, well, it varies. The average rate ranges, and this is quite a big range, from 3 to 300 meters a year, but it can be as much as 1 to 2 kilometers a year. There are some areas of really fast moving ice, particularly when it comes to outlet glaciers in Antarctica. These get called ice streams, and they can move as fast as 7 to 12 kilometers a year. And then there's something else really interesting that happens. There are some ice lobes that advance from ice caps or ice sheets that can surge. And that just means that for some reason we don't understand, they have these phases where they suddenly move much faster than normal, 10 to 100 times faster than they normally move, for really short periods of time, like maybe days, weeks, or maybe even a couple of months. So a reminder now, the glacial budget is the balance between accumulation at the upper end and wastage or ablation at the lower end. And the ice front either advances or recedes, or it's just stagnant. It doesn't do either of those. What about these images on the right? The one at the top is near an ice toe, and there's actually a subglacial stream coming out from under the glacier. Here we can see lots of rock material that's embedded in the ice, but then all this dark material up here is just rocks that have been frozen in to the surface of the ice. And here's someone standing on a gravelly bar that represents sediment that likely has been carried by this subglacial stream. The image in the lower area here shows a valley glacier that's flowing from somewhere back in the distance down towards us. But what you can see here is really pronounced lateral moraines. That's piles of sediment on the ice that have fallen down slope. This image is from New Zealand. And there's more debris on top of the ice on this side. And we can also see a medial moraine. And that tells us that we have at least two valley glaciers that joined to make this one. Okay, so now we're going to shift to looking at continental glaciation and the upper Midwest. We've already introduced this map that we're looking at here. And so the basic story is there was a large ice sheet extending across most of Canada and the northernmost states in the US. And that ice sheet is called the Laurentide ice sheet. It existed throughout much of the Pleistocene. And from the Laurentide ice sheet, a whole bunch of different ice lobes extended to the south. They advanced and they retreated. Now, first thing I want to do is dispel some of the classic ideas of North American geologic or glacial history. In most of the texts that you will look at, you will see that there have been 4 glacial periods identified within the Pleistocene. The youngest is the Wisconsinian, prior to that, the Illinoisan, the Kansan, and the Nebraskan being the oldest. And these get named because these are the states where the deposits associated with what were regarded as those advances are best preserved. Well, now pay attention to the writing in red. This is wrong. There are far more advances than just 4 advances. We know that there are likely at least 16, and it's really hard because the sediment from those older advances ends up many times being buried by sediment deposited by the younger advances. So it's a tricky thing to disentangle and understand. But you will see these names and just bear in mind that, oh, it's actually a lot more complicated than that. And one of the reasons, or we are going to focus on the youngest time chunk, partly because that is the time chunk that produced the landscape features that cover most of Minnesota, and it's what we know best. Okay, so let's just step back a moment and think about what some of the features associated with continental glaciation are. We've got a whole list of features here, and there are many more. People who study glacial geology know that it gets very complicated. What I want to really focus on first is what we call the glacial sediment. Before we do that, here we're in an area in front of a glacier, so a proglacial setting. And you can see some snow here, and then there's basically some frozen sand and gravel there. So all the sand and gravel here is pretty much frozen in place. And it's very difficult and dangerous to walk on, but there is some liquid water moving around in depressions or collecting in small lakes there. So we are going to investigate some of these features. Now, first of all, the terminology, drift, till, and moraine. This gets very confusing. First of all, drift. This is an antiquated word, so don't use it. Now, that being said, it is quite well embedded in the literature, in Minnesota particularly. The term developed because before people really understood glacial environments, they envisaged icebergs drifting around, and as they melted at their base, sediments melted out of them and drifted down to the sea floor. We now know that glacial deposition is far more complicated on land, and this term shouldn't be used. In Minnesota, one hears the terms old red drift, gray drift, brown drift. Yeah, it's embedded in the literature, but most of the newer publications use the words till or moraine. So, what does the word till mean? This is a word that describes sediment. It's just the unsorted sediment deposited by ice. Another word that sometimes gets used for this sediment is diamect. That's because it's poorly sorted and it's usually made up of fine-grained material with large chunks, hence the diamect. Now, the word moraine is far more complicated because it's used in a variety of words. So, first of all, it generally gets used for glacial sediment, in other words, till, that forms landforms that are a result of ice activity. So you will hear the word ground moraine for or for areas of sediment deposited underneath ice in Minnesota, ground moraine. Sometimes you will also hear the word lodgement till. That is the word for glacial sediment that's deposited underneath the ice. There are also ways in which the word moraine gets used to describe where sediment was deposited in relation to the ice. So you may hear the term supraglacial moraine, that or supraglacial till, and that refers to sediment that was originally on top of the ice melted and let that sediment down. Or marginal moraine, lateral moraine, medial moraine. So the use of these terms is complex. The image on the right here shows the remains of, or we're very close to the front of a glacier. And here, once again, we've got a whole load of frozen sand and gravel. We'd call this till, or possibly call it moraine, supraglacial moraine. Here's a little lake on top of the ice. It's a very messy, complicated area. So just look at this and think about how complicated understanding the glacial sediments of Minnesota must be. So, what are some of the landforms associated with continental glaciation? First of all, eskers. Eskers form under the ice by subglacial streams. So here, in this diagram, we've got ice, and there is a subglacial stream. That means under the ice stream. And when that, there's a tunnel that the water moves through, because of the physics of water lifting ice and then not lifting the ice. What happens is there'll be times when those streams are carrying huge volumes of sand and gravel, and then they stop flowing. And when they stop flowing, all the sediment that they were carrying is deposited. So here you can see, I hope, a ridge that is kind of snaking around. That is an esker. And eskers are typically gravel rich. Many of the gravel pits in or small gravel pits in Minnesota are in eskers. That's because they stand up from the landscape and they're very easy to extract gravel from. Another type of feature is a kame. And kames come in all sorts of flavors, so to speak. So technically a kame is coarse material that may include some sand that is either deposited underneath a hole in the ice. So imagine the ice extended all the way across here. There was a hole in the ice. There was a stream on top of the glacier carrying sand and gravel, and it just dropped down those holes to leave these little mounds. Many golf courses are developed in areas of kames in Minnesota. They make very interesting topography. Anyway, the other types of kames are kame terraces. So a kame terrace is anywhere adjacent to ice where water tends to deposit and organize sand and gravel. What you can also see in this diagram is what's been identified as ground moraine. So that'll be glacial sediment. We could call it till that has been deposited by the ice. Two other key features, drumlins and kettle lakes. So what are drumlins? There's an image of a drumlin right here. And over on the very left-hand side of this diagram is a picture of a drumlin field. So drumlins are piles of sediment that were sculpted by the ice. And well, because we can't actually see under the ice as they form, our understanding of the details is kind of limited. But we know that they elongate in the direction of ice flow. So they're these kind of teardrop shaped features. Kettle lakes, which are near and dear to us here in Minnesota. These are the result of what we call ice block meltout. And they're common in what are known as terminal and recessional moraines. So a terminal moraine is a big pile or zone of sediment that marks the farthest extent of the ice. Recessional moraines form as ice retreats, and ice rarely retreats in one smooth, gentle phase of movement. It will retreat in fits and stops. And each time it ends up being stagnant for a while, a recessional moraine will form. So how exactly do the kettle lakes form? Well, there'll be lots of sand and gravel. There will be a very large house-sized or kilometer-sized blocks of ice that get buried in that sand and gravel. Over time, that large block of ice melts and leaves a depression. That depression, such as here, 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 will eventually form a lake. It will be filled by water. Heads up. The water in a kettle lake is not glacial water. It's just water that's there as a consequence of the intersection of the water table with the landscape. Okay, let's take a look at a couple of examples. So you can pause the video here, look at the feature here, and here's an aerial view. There's some quite elongate features here. They're a little bit hard to pick out. What do you think they are? These are drumlins, and there are several drumlin fields. That's when there's a whole bunch of drumlins really relatively close together in Minnesota. Okay, what are we looking at here? These are both aerial views. I want you to draw your attention to this feature here and this feature right here. Okay, we're looking at eskers. I believe this is, I can't remember the name of the big esker in that runs kind of north-south in Canada. I think it might be the Barron's esker. Anyway, they often act as highways for animals because everywhere in the low-lying areas are really swampy. The eskers are more upstanding. They're made of gravel, so they become animal highways. And here we are off the northwest coast of Scotland. I'm not giving you an answer here. There's lots of features that I think or hope you might be able to identify. So another thing that's very important is getting our brain around some of the terminology that gets used. You've heard me using some of it already. Here we've got the ice front. So everything that happens in front of that gets called proglacial. And so here we have a whole bunch of proglacial lakes. And you can see a bunch of other features that have developed in here. There's some ridges, etc. If something happens on top of the ice and gets somehow preserved in the landscape, that's a supraglacial feature. And then under the ice, we talk about subglacial features or processes. So proglacial is what we're featuring here. That means in front of the ice. And it's a very messy and dynamic area. And as you can see, it's likely to be modified by streams. Okay, so now let's focus on the history of ice slope advance and retreat in Minnesota. So if we look over to the right at this image taken from the NGS Minnesota at a Glance leaflet, the gray area represents the Laurentide ice sheet, and then over to the west in British Columbia into Alaska, we have the Cordilleran ice sheet. But what's important for us is that there were two ice centers, the Labrador Dome and the Keewatin Dome. So there were these areas of much thicker ice. Ice basically moved away from those domes in all directions. And just because of climatic variation, they were active, not necessarily completely in sync, but they sent ice southward as well as in all the other directions. So we have if we move over to the left, we have our two ice centers, the Keewatin and Labrador domes or ice centers. And throughout the Pleistocene, ice lobes advanced from each of these centers. Well, and look at this, guess what? Minnesota is just amazingly located. We, over time, have received ice that essentially was sourced in the Labrador Dome, and it came from the northeast of Minnesota, and the ice from the Keewatin Dome came from the northwest. Well, that's very interesting. But what's really fascinating is ice from each of these sources traverses really distinct bedrock, and therefore the ice ends up carrying, transporting, and then depositing very distinct range of rock types. So when we look at the glacial sedimentary record in Minnesota, we can identify deposits that were derived from the northwest versus deposits derived from the northeast. So let's take a little look at this. So we are going to focus, as I mentioned before, on the Wisconsin. And essentially that represents the time chunk from 75,000 years ago to 11,000 years ago. And then more recently, once the ice really melted, glacial Lake Agassiz, and glacial Lake Agassiz was enormous. I've got some maps we're going to look at in a moment. It was more than 300,000 square kilometers, contained more water than all the Great Lakes combined. Anyway, let's look at the diagram on the right. The most recent ice lobe to move south into or across Minnesota and North Dakota as well, and down into, well, Kansas, Iowa, is the Des Moines lobe. So it came from the Northwest, and that also gets called the Winnipeg provenance, or sometimes the Riding Mountain provenance. And it extended all the way to Des Moines. The terminal moraine is just outside Des Moines. It has a couple of sublobes associated with it. There is this higher ground here that actually represents deposits of earlier ice advances that the ice wasn't able to sort of surmount and move across. So we have the main Des Moines lobe. There's a little offshoot here, the Grantsburg sublobe, and then further up to the north, we have this St. Louis sublobe. So that's the most recent ice lobe that moved southward across Minnesota. As we go back in time, there's the Superior lobe and Rainy lobe. The Superior lobe effectively moved through what is now Lake Superior. It gouged out all the volcanic and sedimentary rock related to the mid-continent rift. There was already a slight depression there, which facilitated the movement. And then that Superior lobe deposited what is the St. Croix moraine. So that's the area in this sort of slightly reddish color here. And that also includes, or at the same time, there was the Rainy lobe moving more directly from the north. The oldest ice lobe associated with the Wisconsinan is what's called the Wadena lobe, and it moved, you can see an arrow here, in a southwesterly direction, and is responsible for what's called the Alexandria moraine. So those are our ice lobes in the Wisconsinan. Now let's just think about when the Des Moines lobe melted. That meltwater basically filled up Glacial Lake Agassiz, shown here. This is Hudson Bay. Here we have Minnesota. And Glacial Lake Agassiz drained in different directions, shown by these red arrows. Hudson Bay to the northwest and up towards the Mackenzie River, southward down the Minnesota River, and then into what is the Mississippi, and then at various points through the Great Lakes out into St. Lawrence. Absolutely enormous. So what's of particular interest to us is, yes, there's the very flat areas up in northwestern Minnesota. They effectively were the lake bed associated with Glacial Lake Agassiz. But when the lake broke through a moraine dam here in Browns Valley, it basically sent a huge glacial meltwater river known as Glacial River Warren down what we now know as the Minnesota River Valley, shown in red here. So that's the melting of the Des Moines lobe on Glacial Lake Agassiz. So the map here is from the NGS Minnesota at a glance that take a good look at this, pay attention to the detail. What I want you to take away from this is the glacial sediments associated with Northwest derived ice are largely shales from the Pierre Shale, which is Cenozoic shale in the Dakotas up into Canada, a lot of limestones and granites and metamorphic rocks. This Northwest derived sediment is generally pale colored, gray, and clay rich. On the other hand, Northeast derived ice, such as that makes up or made up the superior lobe, gouged out the mafic volcanic rocks amongst all the other volcanic rocks of the mid-continent rift, together with some granites and metamorphic rocks. And the iron-rich volcanics mean that it is red-brown in color, and it's also sandier. So that's a really quick trip through glaciation in Minnesota. And in the D2L, I've put a whole bunch of links. There's a primer on glacial geology landforms and ice lobes put together by Minnesota DNR. And there's also a really good section on the Minnesota Geological Survey webpage about glacial geology. You'll recognize this diagram, and there's a lot of information there. They've got some good pictures as well. I've also put the Minnesota at a glance handout into D2L. So enjoy exploring Minnesota glaciation. That said, I'm going to stop, and next week we're going to investigate fracking and silica sand mining. Bye.